I hope that you've had a chance to take a tour of the universe and have a little idea of how it's composed and of how the sizes of things in the universe contribute to the kinds of things that they can be. I'd like to take a little bit of time now to go through the different fields of learning within the natural sciences and show how in each field there's a specific question that's of great cultural importance that is commonly presented in a secular manner, not because the secular position is true, but because the secular position is just what's being presented. When we are teaching our own children, we need to be alert to what these questions are. These are not science questions as such. They're philosophical questions. Or in some cases, there is scientific evidence, and when there is, it's on our side, of course. The first question is there a universe? And you might be thinking to yourself, well, that's an easy one. We have a universe. But a universe implies a unified material universe. And that's what's in question when people talk about multiverses or when they talk about an infinite universe. Pretty much the infinite universe is a dead theory now. But the multiverse idea that you get from Stephen Hawking is a rebirth of the infinite universe, an effort to somehow escape from the idea that this universe is really unique, special, planned, intelligent, given to us by our Father. And when we are reading the natural sciences and when we come to questions of cosmology and when the question of multiverse comes up, here are some considerations. First of all, if you really are a physicist, you can read Robert Spitzer's book, New Proofs for the Existence of God. But if you're not a deep physicist, let me just give you the simplest things. First of all, either there's one universe or there's two or more. If there are two universes, then either they interact or they don't interact. If two universes don't interact, then there is no way for us to know about the other universe scientifically. And therefore, it's not a scientific discussion to talk about it. You could have a philosophical discussion, but scientifically speaking, we are talking about things that can be measured, weighed, and counted. And if there's no interaction between us and another universe, then there's nothing to be weighed and measured. Part of this question really comes from the early part of the 20th century, when the dimensions of the Milky Way became clear. And then we began to see that there were other things out there that were outside of the Milky Way, and we began to talk about them as island universes. But they were island galaxies, and they are interacting with us and with each other. First of all, if we see them, they're sending us light, so that's an interaction. But secondly, we began to see that different galaxies were rotating around each other and doing all kinds of stuff. The galaxies are interacting in a single universe, which has a specific size. So that's the first issue. Is there a universe, a single collection of material entities that are just interacting with each other? And the answer is yes. So this is an image of the universe in God's hands. And if we take a billionth of that universe, we're talking about a very interesting fact about the universe, which is that at a certain point, again, probably 50 years ago or 60 years ago, the impression was, okay, there are a lot of galaxies out there, but they're all just sprinkled around like salt on your eggs. They're all sprinkled evenly, they're all exactly the same, or maybe there's two kinds or something like that. Not a feeling that the universe beyond our immediate neighborhood had other points of interest to it. Always a feeling, a very secular, typical feeling that, we've really learned everything that there is to learn and the rest of it is boring. No, it's not. Every single galaxy is unique and fascinating, and at this level of 1/billionth of the size of the universe, we actually have collections of galaxies with great voids between them, 500 million light years across, outrageous distances of absolutely nothing, and then other ways that galaxies are collected, implying that there are dimensions of structure out there in the wide universe that we never would think of if we just stuck close by our own neighborhood. So, rule 2. Rule 1, there is a universe. Rule 2, it's interesting. The parts of the universe you don't know anything about are interesting parts of the universe. And when you find out what's in them, you'll be fascinated. This here is a picture of, or an image, of the Sunflower Galaxy. Just to remind you, not all galaxies are the same. And here's what's important about the differences between the galaxies. When we come to talk about life in the universe, and whether there's life in other galaxies, you might say to yourself, oh, if something is 2.5 million light years away, how could you possibly know whether there's life there? Well, here's what you need for life. You need time to evolve. You need to go one step at a time, as we have. If you read, there's things you can read that will show you what the requirements are for life. In a galaxy where the stars are too close together, even like the Andromeda Galaxy, our near neighbor, which is an elliptical galaxy instead of one that has spiral arms on it. In an elliptical galaxy, the stars are mostly close together. What's the problem with stars being close together? Here's the problem. The big stars have an explosion in their lifetime called a supernova. Now, a supernova means that the star comes to a point where it's hot and it's all blown up and its gas is all the way out here, and in the center it can't burn anything anymore, so it's kind of cooling down. And all of a sudden, it just hits that moment when it's cool enough that it's no longer able to hold all this other gas up here as steam. And all of a sudden, the whole star that's way out as far away from the star as Saturn is from the sun collapses down at once, smashes into the star, breaks back out again in a great bounce, and creates all of the high elements on the periodic table. Now, these explosions, let me explain something. This is a nuclear explosion. This is as if the whole entire star exploded like an atomic bomb. But remember, an atomic bomb is not very big compared to a star. So here's what it's like. It's like 2,000 billion atomic bombs exploding all at once. It's a very big explosion. The explosion of a supernova is so big that in the first minutes or days, as we would measure days, of that explosion, that star, that exploding star, that supernova is brighter than its entire galaxy. It's a massive explosion. So, again, a very interesting thing. And it's just like other explosions in one way. Namely that when something explodes, you don't know exactly where all the shrapnel is going to go. It goes every different direction. And so every supernova, where we have pictures many years afterwards of that part of the sky, it's all full of debris in all kinds of interesting shapes. We have the Crab Nebula, and we have all different shapes. So a supernova is a fascinating event, it's a rare event, and it's an incredibly bright event. And it's the event which allowed all of the elements on the periodic table above 26 or 27. We can get up to iron without a supernova. We can get a little bit of nickel, but we can't really get much farther. No uranium. And you may think that uranium is not important to you, but actually it is, because here's why. If we had no radioactive elements in the Earth, the sun would not be able to keep us warm enough. We get about 25% of our heat from under our feet, not from up above. So our Earth, in its center, and also in the chromium that helps us digest our sugars, and also in the gold that's in all of our wedding rings, That is all from a supernova. All of those things are from a supernova. We are a post-supernova civilization. So, always something interesting to learn. Inside the galaxies, there are different arrangements of stars. We ourselves, naked eye, are only seeing probably a billionth of our galaxy. And the reason is that the galaxy is 100,000 light years across, and you just can't see that kind of a distance. There's dust out there, but also the light from a star becomes attenuated when it goes over these huge distances. So here's a picture of Orion, and most of the stars in Orion are within 1,000 light years. Most of the stars in the Dipper are in the area of about 100 light years or 150 light years away. 5 of the stars in the Big Dipper are actually traveling together. The other 2 just look as if they're connected. And so those are the kinds of distances that we're talking about. We're seeing maybe a billionth of the universe. Now, this here is the Cat's Eye Nebula. Once again, I want to say, I've talked to you a little bit about a supernova making this massive explosion, but that's at the tail end of the life of a large star. There are some stars that aren't quite that big, and they never are going to get to a supernova, but they do get to a point where they expand and put out all these gases and make a big huge circle of gases all around themselves, and then they cool off in the center and kind of collapse down, but some of this gas is left out here at the edge. And that gas that's left out there is illuminated still by this little ember of a star in the middle. And which gases are out there, depending on the life of the star, depending on where it is in its burning cycle, and just depending on stuff. There can be all different gases, and so each planetary nebula, that's what it's called, each circle of gas illuminated by this coal in the center, looks different. We have the Eskimo Nebula, and we have the Cat's Eye Nebula, and we have the Spirograph Nebula. If you want to be inspired to make a bunch of beautiful pictures that are more or less abstract but beautiful, just run your search engine on planetary nebulae. Just an amazing collection. So this one here is called the Cat's Eye Nebula, and we're looking at something that's maybe 1 or 2 light years across. Let me talk to you about a light year. I'm sure you've heard that a light year is the distance traveled by light. It's not a measurement of time. It's a measurement of distance, and the time frame in there is just because we're trying to get big numbers, because we need big numbers to talk about the universe. A light year is about 6 trillion miles. So if I say the Cat's Eye Nebula is 2 light years across, it's 12 trillion light years across. It still is an unimaginable distance. And a billionth of this area would be, a billionth of the middle of that actually, be the size of the solar system. And the solar system is, the sun, and in this case I'm talking about the sun and the planets out to Jupiter and Saturn. I'm not even going all the way out to Pluto necessarily, but we're already talking about 600 million miles. Let me just give you a little historical note here. It's well known that Copernicus said that he thought that the planets were going around the sun. What's not so well known is that the people who opposed him, of course there were some who opposed him because they said, the Earth has to be the center of whatever. Other people opposed him because they said, oh, wait a second. If the planets are going around the sun, that must mean that they are huge distances away, like 70,000 miles or something. No, it isn't 70,000 miles. It's 600 million miles. It's a distance that is unimaginable. You're not imagining, you're just hearing words. But in Copernicus' time, they were imagining it, and they were understanding that his proposal, which was still way smaller than the truth, was a complete change of thinking. So Now, when we talk about the solar system, though, there is another issue that comes up in relationship to the solar system and the stars, and that is, how common is it to have a solar system? Well, there are 3 trillion stars in the Milky Way, and a trillion or 3 trillion in any of the other galaxies, and there are trillions of galaxies. So there ought to be lots and lots and lots of inhabited planets, lots of stars that could have inhabited planets. And as a matter of fact, Carl Sagan, who's very, very smart and very, very pagan, said that at one point, well, there's probably about 10,000 inhabited planets in the Milky Way. So this has been quoted over and over and over, as if he would ever know such a thing. But in the 50s, somebody named Enrico Fermi said, where is everybody? If there's 10,000 inhabited worlds, where are all those inhabitants? We should be able to see them. One thing that you don't understand until you talk to somebody who knows about these kinds of things, but you understand how far away you can see a single candle. You have probably read stories about World War II where they said, when we're having a blackout, don't you dare go outside even with a cigarette, because it's so visible. Well, using the instruments that see radio waves, our planet is bathed in radio waves all the way around. It's lit up like a Christmas tree. And anybody who can see our planet whatsoever knows perfectly well that on this planet there are people who are using television and radio waves. That's visible. And anybody who had an advanced civilization would discover those things. And they'd be using them too. And we could see them. And so Fermi said, where is everybody? And then there's this big search for extraterrestrial intelligence. But here are some of the problems. Sure, there are lots of stars. But all of the stars that are towards the middle of a galaxy are around other stars which are having supernova explosions. Not very often, but a supernova sterilizes everything within 30 light years. So nothing in the remote neighborhood of a supernova has life. So if life takes 4 billion years to develop, the only place where there can be life is a place where there hasn't been a supernova for 4 billion years. Okay, that cuts out, it cuts out almost all of the Andromeda galaxy. It cuts out a huge amount of the Milky Way galaxy, and similarly all the way through the universe. So now all of a sudden we're down to, I don't really know what, a 10th or a 100th of what we thought we had. You also can't have life on the outermost part of a galaxy because the stars on the outer section are older. And if they're older, then they may not have a long enough life ahead of them to have life, because life takes billions of years to develop, and you have to have, during all of the period of the development of life, you have to have a planet that has water on it. Water, that's such a tiny temperature range. Stars are way too hot. If you get anywhere close to them, they're way too hot. If you get too far away, you're immediately in this wicked cold vacuum where you can't do a thing. So the realm for life, called the Goldilocks realm, not too hot and not too cold, is very, very small around any star. And it changes rapidly if the star starts going through rapid changes. So there's no life on the outer part of any of the galaxies. And there's no life on the inner part. There's just a little Goldilocks ring where you could have life. That's just a couple of the conditions. Another condition that's kind of interesting is that the planets have to go around the star pretty close to in a circle. Because if they have an elliptical orbit, a very elliptical orbit, then you're going to have, at one end or the other, it's either going to be too cold or too hot. You can't maintain the temperature that allows water to be liquid unless you have a pretty round orbit. And in case you don't understand why water is important, let me just stop and say, water is the universal solvent. In order to have a living being, you have to have something that is able to grow and develop and be nourished. And that means a circulatory system, and that means water. That's really why that's important. Now, let me just tell you one more condition of life, because it's kind of an unexpected one. Probably also a subduction, continental subduction, is necessary for life. And here's why. There are different ways that carbon is sequestered by life. We have, on our own planet, we have trees, they grow. If the trees fall down and just get buried, then you keep on sequestering carbon like that. And pretty soon the planet starts to get cold. And you can have what's called runaway ice house. We think we had a runaway ice house on Earth about 600 million years ago. 600 million years ago. The Earth was getting very cold, and it looks as if it was about to become so cold that it would never be warm again. But what had happened was that there had been subduction of one continent under the other, and the continent that went down under had heated up from the center of the Earth, because it's radioactive down there and other stuff. It had heated up and melted and begun to bubble up, and finally it pierced through as volcanism and returned the carbon dioxide to the sky, and things warmed back up again. And this is really a periodic function. Things get hot and cold over the life of the planet, but that subduction, if it works in the way it's been working in the last 600 million years, it happens often enough to keep a kind of a sort of constant replenishment of the carbon dioxide, sequestering replenishment. And so that's an essential for life. It's one more way, one more mechanism that has to be in place in order to keep the planet hospitable to water and hospitable to life. So it's not a small thing to have a planet with life on it. If you read Warden Brownlee's Rare Earth, or if you read Guillermo Gonzalez's book, Privileged Planet, you get just a whole bunch more fascinating pictures of what's essential for life. And when you say, this condition for life is likely to happen in 10% of the universe, and this is likely to happen in 2%, and this is likely to happen in 4%, and this is likely to happen half the time. When you add those all up and multiply, the number gets smaller and smaller. A half times a half is a fourth, and a fourth times a fourth is an eighth, and multiply that by half, and it's a 16th. Pretty soon, when you add up all of these conditions, you have so many conditions limiting it so much that, mathematically speaking, chances are there's just one inhabited place in the whole universe. In fact, chances are there's none, but we know there's one, so we won't need to go there. But just to say, the idea that life is common, which has been going on for 400 years, there's no evidence for it. There never was any evidence, and there isn't now either. So that's what we need to know about stars. A billionth of the size of the sun is the size of Ceres, which is one of our asteroids. The interesting thing about Ceres, which is about 100 kilometers in diameter, is that it seems to be probably just about the smallest thing that you can have, which has enough gravity to pull itself into a sphere. All of the other asteroids that we have are sort of bean-shaped, they're sort of potato-shaped, but this one is round, and in fact you probably think this is a picture of the moon, but it's a picture of Ceres. Quite different. Indistinguishable, unless you actually know the geography of the sun, of the moon. But and a billionth of the size of Ceres would be the size of some of our mountains, some of our small mountains. This is the Arena volcano in Costa Rica, but mountains in general are in this neighborhood of a half a mile high, maybe a few miles high. We know that Mount Everest is 5 miles high, but it's not 5 miles high rising out of the sea. It's 5 miles high with, plateau all around it. So let's take a minute to talk about the issues that arise for the culture of life when we begin to talk about geology and when we begin to talk about meteorology, because those are the large-scale disciplines that we still need to talk about. In geology, the fundamental issue, which is a non-issue for Catholics, is geology really enforces clarity that the earth has a great age. If you just talk about rivers and how they flow and the water cycle and that sort of thing, then you're okay. But sooner or later, a geologist is going to notice that the sand is there because the mountain is eroding. So if we have a sandstone deposit here, that means a mountain of the past eroded, and it's gone. It's gone completely. Where did it go? How long does it take to erode an entire mountain? More than 6,000 years. We just are not in that time frame. Well, for myself, I just want to say very clearly to a Catholic audience, the Bishop Ussher, who said that the world was 6,000 years ago, and that's what Scripture said, was an Anglican bishop. And he was able to enforce his opinion within the Anglican community, and then other Protestants took it on. It is not a Catholic teaching. It never was a Catholic teaching. The father of geology is a canonized saint. His name is Nicholas Steno. And he understood, he might be 100 years after Bishop Ussher, but he understood very, very clearly that what we're dealing with is huge amounts of time. Whole mountain ranges becoming eroded. So this age problem is not one that we share. And I want to say something else kind of interesting and fun about the age issue. In Germany, or Austria, and anyway, there's a statue called the Lindworm, the great dragon of Lind. And of course there's stories about it, but the bottom line is that the head is based on a fossil that was found in the area. And the fossil we now know and can identify, it's the woolly rhinoceros. But those people didn't know about woolly rhinoceroses. What they knew was, once there was an animal here that isn't here anymore, it has absolutely never been seen by anybody here. And so they made this statue, which is fantasy, but which expresses the fact that the fossils were always there. They weren't discovered for the first time in 1850. They were always there in the ground. People always looked at them. St. Augustine looked at them, and he said, oh my goodness, the sea must have been completely differently distributed in the past because the fossils go so far inland in Italy. In fact, you probably didn't know this, but if you go into a church in many places where there's marble in the church, and if you look at the marble, you'll see little fossils in the marble that come from the sea creatures that were squashed together to make limestone into marble. So the fossils are there. They've always been there. People have always seen them. And it's okay for the earth to be old. We're not committed to a young earth. A different issue comes up in meteorology. And meteorology is the study of weather. And the different issue is this. We are now at a moment where the textbook teaching of all of our children, repeated in their history class, in their science class, in their literature class, is that we men are destroying the earth by causing global warming. Really, this is an abusive message to give to the children because it makes them feel ashamed of being human beings. And it's just silly. Let me talk to you about global warming. 20,000 years ago, there were glaciers halfway across South Dakota and most of the way down the Hudson River and all across Germany. Thank heavens there's been global warming for 20,000 years, and we are where we are and can live where we live. And the glaciers have continued to recede at an average rate of a mile a year ever since 20,000 years ago. So what's new? What's new is an impulse to tell people not to have children. In the 1970s, it was thought that the globe was cooling, and the proposed solution was fewer children. Now we've decided that the globe is warming, and the proposed solution is we shouldn't have any more children. It's wrong. It's wrong to tell children that they shouldn't exist. And you need to understand, children are not like adults. They don't have a whole understanding that there are political winds going this way and that way, and everybody has a different idea, and all kinds of different stuff is going on. No. Children are being told in the lower grades, it would be better if you didn't exist. That is a wrong message. That is totally opposed to the culture of life. And in fact, of course, by the time they're in high school and college, they're thinking that, oh my gosh, a moral person would not have children. And, okay, I think I've said enough about that. but I guess I can say one more thing. We know a lot about weather, but there may be larger cycles that we don't know about. We still are facing the El Nino and La Nina, and we don't know what's causing them. Well, I know somebody, because she's in my family, who believes that those things also have a specific cause that we could investigate. And she's done some very interesting work, and you can look her up on YouTube, Lucy Hancock, but you can look up Lucy Hancock Earth Rings. But here's what's interesting. Nobody will follow up on her work. Over and over again, she meets people who say, oh, that's really interesting. And then she says, and then I can see them think, this is really interesting, I should pursue it. And then all of a sudden, their face changes. What will happen to my career if I start saying that global weather events are not caused by men driving cars? And as that look comes over their face, they turn around and go look at somebody else's exhibit. They can't afford to follow. So it's a highly political issue, but it's also an abusive issue, and it's also a profound cultural issue. Now, next step down, we come to the issue that everybody knows about. It's very, very simple, and that is the issue of human life and of evolution. Of course, evolution, everybody knows that that's a cultural issue. But I want to say a few things that aren't very often said. Evolution, in the sense of change over time, is clearly something that has taken place. That's one of the clear messages in the geologic column. We see that when we go down very, very deep, if I would dig a hole right underneath where I'm standing, you would go down to a place where there were no fossils. Then a little higher up there are places where there are fossils of fish, but no land animals, and so forth. So there is a geologic column. It does imply a history to life. That's not a problem. Problem comes when you ask the question, how do new species arise? And Charles Darwin, kind of going off the fact that every farmer tries to improve his apples and his pears and his horses and his dogs, said, well, Mother Nature's been doing that over billions of years. Whoops! Mother Nature doesn't have billions of years to improve horses. It's 500 million years since all of the bony creatures, or at least the bones of the bony creatures, came onto the scene. And all of the vertebrates have developed since then. So we have 500 million years. And here's what's even more interesting. If we just look at the vertebrates, because that's what I can be simple about. The first vertebrates were the agnathans. Then there was another called the placodonts. Then there was another one, the sharks and the fish that don't have bones. And each new phylum in the vertebrates arose in the youth of the previous phylum. And so in the youth of a phylum, there's a new thing that comes off, and then the phylum develops forward, and it develops all different kinds of agnathans, all different kinds of placodonts, all different kinds of sharks and fish, cartilaginous fish. But it never goes back again and gives birth to a new bony fish. And in fact, all of the placodonts died out, and they were never re-evolved. And almost all of the agnathans have died out. There's 2 basic species left, or maybe 2 genuses left. That's it. It's gone. Evolution has stopped for these guys. It's over for these guys. They're all dead. No new cartilaginous fishes. No new bony fishes for, I think, 200 million years. And so forth. So we want to get the amphibians, we get the reptiles, and the youth of the reptiles apparently is when we got the mammals, and we have the birds. But as each phylum moves out of its youth, it loses the creativity, the big creativity that allowed it to produce another phylum. And now we're at the point where the last vertebrate phylum to come out is the mammals. And the mammals are, all of the zoo creatures date from between 5 and 30 million years ago. And then at the tail end we have man, and it's over. There are no new mammals. It's finished. Evolution is over and finished. And not to face up to that means that you're not really talking about what the record says. The record says there was a movement, there was a creativity, and it's over. So now, let's talk about, and is there any way of dealing with that? First of all, let's talk about Darwin. As I said, he's going off the farmers, and he's imagining that one little change added to another can eventually get to be a big change, which is a reasonable suggestion. But it's not actually a suggestion that will give you a new genus or necessarily a new species. That is to say, if I change one gene in your makeup, you might have a crooked finger, you might have a crooked nose, you might have black eyes, but you'll still be a human being. To make a change so radical that you actually have a new species which can't reproduce with the old species, one gene at a time doesn't do it. You need to change the chromosomes. And somebody named Ruth Manton was the first one to work this out. She worked it out in relationship to ferns, which are very different from animals, but anyway, you can easily chop them up and work with them, so I guess that was what she did. And besides that, she was in New Zealand, so the Darwinian establishment didn't get on her fast enough to knock her out. So, in order to have a new species, you need a new chromosomal arrangement. But that creates a problem. And the problem is this. If I, as a woman, get a new chromosomal arrangement, then I will have no children unless I can find a man who has the same new chromosomal arrangement. For me to get a new chromosomal arrangement that's viable is a long shot, but for me to get it accidentally, while a man in the neighborhood also gets it accidentally, is beyond that. That's just unreasonable. There has to be another mechanism. So somebody named John Davison, professor of zoology at the University of Vermont, has made a proposal, and the proposal basically is that when you get this deepening commitment to sexuality as the form of reproduction, that it becomes more difficult to get a new species. You have to have individual episodes of asexual reproduction in a species that normally reproduces sexually. This is called parthenogenesis. People have studied it. It can happen. It's not common, but it can happen. And if you have parthenogenesis, then you can have, I get my chromosomal rearrangement. I have a bunch of eggs that have this same chromosomal arrangement. And then sperm can come and not contribute their genetic material, but just initiate development and back out. That's the way parthenogenesis works. And then I have a bunch of offspring. And then, in case you know enough biology to think this thing through, you might say, well, then they would all be female. But first of all, the female genome has all the information necessary to make the male. And secondly, this does happen occasionally, and so we can study it, and there isn't any other way to do it. You have to have this single episode. Not only for man, you have to have Adam and Eve elephant, Adam and Eve, and Adam and Eve have to be the two children of this one female who had an unusual episode in her germplasm. So there is a proposal out there that will allow you to have new species from old in one generation. And that's what's interesting. The geologic column shows us that new species turn up abruptly. They don't just turn up gradually. They turn up so abruptly that it becomes a question, how can this happen so fast? And the answer is, if you do it by semi-meiosis, which is the name of John Davison's theory, then you do it in one generation, and that's fine. And the mother herself is the old species, and the children are the new species. So that's the only proposal that's out there. You can't do it one step at a time. You never can. And in all of the history of evolution, this is very interesting. There is no example of evolution going backwards. Now, you would think if it goes forward by accident, it could drift backwards by accident, but it never does. Even if the weather changes or the climate changes, so that there need to be changes in the way that the genome is expressed, and then if the climate changes back again, the genome doesn't go back the way it was. It goes forward to a different place. The book to read about this is called Basic Questions in Paleontology. Fascinating book. But the sum of all of these things is that evolution is not just an accidental collection of events. In some sense, in some way, there's a plan or a blueprint that's unfolding. Now, let me talk about that unfolding. When we say that evolution implies intelligence and that it's unfolding like an intelligent thing, that doesn't necessarily mean that God has to intervene and twiddle with the genetic material to make things go forward. That's not what we're saying, and it isn't necessary. Go back a minute to the way that the periodic table comes out of the stars. If you look at the periodic table in your chemistry class, you'll see hydrogen, 1 proton, 1 electron, helium, 2 protons, 2 electrons, some neutrons, lithium, 3 protons, 3 electrons. So you say, oh, I can see how to build a periodic table. Add another proton, add another electron, squish in some neutrons if I feel like it. That's the way you build a periodic table. That's not actually what happens. The periodic table is built inside stars, and you go from hydrogen to helium, and then you go from helium to carbon, and some of the carbon is unstable, and that's how you get the stuff in between. And then it goes from carbon to silicon, and some of that's unstable, and that's how you get the stuff in between. So you can imagine a step-by-step for the periodic table, but that isn't really the way it's done. But those 100 or so elements that we have, that's what's possible in the periodic table. You can't have element 45 and a half. You can't have element 3 and a half. These are the 100 things that are possible. And so it's not really unreasonable to say that the same thing could be true in the world of plants and animals. That is to say, there could be like a periodic table of plants and animals where some things are possible and other things are not possible, and the number of possibilities is huge, but it's not infinite, and it can come to an end. And it can also come to a most beautiful place where you have an animal with a brain that's able to carry on certain kinds of functions that allow consciousness and freedom. It's really an amazing work. So when we talk about evolution, the thing that we need to be clear about is that evolution as a history of life is completely reasonable, compatible with Christianity, with Catholicism anyway, no problem. Evolution as a totally accidental collection of events leading to things which are beautiful and complex and amazing. And that's philosophically ridiculous, but also it's not in accord with what we see, either in the geologic column or in the lab when we try to figure out what kinds of things can happen. So here we are with life. We have a billionth of the size of the Reno volcano is the size of people, and a billionth of the size of a person would be the size of a flea. And that's the realm of life. We can give you one more thing in the realm of life, and that is the size of a chloroplast what's interesting about a chloroplast is that it's almost as if a bacterium had gotten caught inside of a larger cell, because the chloroplast is what makes the sugars. It's what collects the sun and makes sugars for the plant. Without the chloroplast, the plant couldn't do very much. It can do a little bit. We have fungus plants, which can burrow into the rocks in a place where chloroplasts can't go. But until the chloroplast gets inside of another cell where it can be protected from the elements, you don't have the big green plants. But the necessity for life really belongs to this size range. And it's an interesting necessity because it has to do with a water requirement and a circulation requirement. So we grow from little things to big things. And inside of the cell we have the molecules, and the molecules are all made, okay, molecules, people are about a meter tall, not usually a meter wide, thank heavens. The flea is a billionth of that, the chloroplast is a billionth of that. So we're going down in size. But when we come to the level of molecules, another whole issue arises. This molecule is 10 to the minus 9. 10 to the minus 10th, which would be kind of in between here, is the size of all of the atoms. And I need to say just a little bit more about atoms. Atoms are made with a proton and an electron. The prevailing teaching is that the motion of the electron around its proton is random. Where have we heard before that the foundation of something which is beautiful and ordered is something which is chaotic and random? This is irrational. Definitely the electron doesn't go around like this, the way it's often pictured in books, because of course if it did, then the atom would be flat like a penny and you couldn't build a three-dimensional body as we have. But here's what really happened. The electron basically goes around its proton at something close to the speed of light. And so you might say, well, how can we get a picture of the electron? Well, here's what the problem is. A light wave is about 10 to the minus 6. A light wave is just about the right size to go to a chloroplast, which is 10 to the minus 6 meters. An electron, or an atom, is 10 to the minus 10th, and so the electron is smaller than that. And so if you send a light wave in there to take a picture, it's just going to hit the electron and push it aside. It's not going to bounce back and tell you where the electron was. That's what you need. So we can never quite see where an electron is. So we know that in some way the electron is orbiting the proton. And we know that that can't just be a round orbit like the planets around the sun. And we also know that we can't take a picture of where the electron is ever. And so what we have to do is we have to say, well, it's somewhere in this area, and we can assign probabilities to how probable it is that it will be at any given place. You know, in an atom, the proton sits inside the atom like a BB sitting in a football stadium, and the electrons are somewhere in all the rest of the space. It's an unimaginably large amount of space that the electrons have to fill. And so we can assign a probability, and that's the only way we can work with it. And so some people said, well, you know, let's just say the electron is infinitely small, and it's just a probability cloud. Okay. It's not a probability cloud. Just because you can't measure it doesn't, in fact, let me say it this way. Just because you can't measure something exactly doesn't mean it doesn't exist exactly. It exists. It's going in an orbit. You can't find the orbit, that's your problem. But to say that an electron is only a probability field, that's a philosophical statement. Because now you're taking away matter, and that's the way all the textbooks say, oh, when you get down to the subatomic level, it's not like our ordinary world that you live in, because it's just a probability field. Really. So our life, where we live, where we bump into each other and touch things and make stuff, is real. But down at the bottom, it's all just a probability field. But here's the problem. If it's a probability field down at the bottom, it's a probability field at the top too. And that is not a fact which escaped everybody's notice. There's a famous paradox, or joke really, called Schrodinger's cat. And somebody said, okay, Schrodinger, so suppose we put a cat into a box. And suppose that we put a lever on the box that will release poison and kill the cat. And suppose that we set it up so that when the electron reaches this point in the orbit, the poison is released. And then we close the box. So the electron is only a probability field. Will the cat be killed or not be killed? And he says you have to open the box to find out. But of course, you yourselves know when you open the box, either if the cat is dead, he's been dead for a certain amount of time. And if he's alive, he never was killed. So the idea that it's just a probability field, no, it's a thing. Things happen. And people went to Schrodinger after they had this fun with the cat, and they said, so, okay, if we look up at the moon, we all see it. If nobody looks up at the moon, is it still there? No. So that's where we are. We're at a point where what we're saying, and it's much more complicated than I can explain here, but it's philosophically very simple. What we're saying is, things aren't there until somebody observes them. So, how do I make you well? I imagine you well. And everybody knows that people get well faster if they imagine themselves well. So if enough people imagine them well, maybe they'll all get well faster, and maybe if we all clap, Tinkerbell will come back. And that's really the level at which this whole philosophical edifice is being built. And it's in all of the textbooks. Within the culture of life, we say, no, it's not an accident. Just because you can't measure it doesn't mean it isn't there. It's there. In chemistry, there is one person, there's probably 100 people or 1,000, but anyway, one that I can name, Joel Williams, who worked at Los Alamos for a long time and very respectable. He's a chemist, he's written a lot of stuff. And in particular, he's now written a book called Rethinking the Atom. It's for sale on Amazon, in which he discusses a specific orbit for the electron. And he explains how this way of looking at the electron satisfies all the conditions that we know about in chemistry, with which he is fully familiar. But instead of being an irrational supposition of probability, it's a very specific idea. And so now, when we come down here to the very bottom of the universe, we see that the question, is it real? Is it chaotic? It's the same question all the way up to the top. Is there really a universe? Are the stars just scattered out there, or is there an order to them? Is there some picture of providence out there? We get to evolution, oh, it's just all irrational accidents. No. Then we get down to chemistry, and we get down to the atom, irrational accidents. All of those questions fall into a class. That is the culture of darkness. The culture of life, the culture which talks about meaning and value and beauty and reality, is our culture. So that's what I had to say.